Okay, I'm calling this video Making It Count. I'm going to show you how to do a 4-bit binary counter. The idea here is you have 4 information bits. Let's call them A, B, C, and D. And this video is picking up where it previously left off. We were doing a 7-segment display decoder, which assumed you had a 4-bit number, and we were just using switches to produce the number. So I'm going to show you now how to make a circuit that will automatically count up in binary. So it starts out with all of them off with the number 0, and then that least significant bit goes on for 1. That's 2, 3, 4, 5, 6, 7, 8, and we're going to stop at 9. Because what I have in mind is a decoder that's automatically counting up from 0 to 9, and then it can switch over to the next 4-bit binary number. Okay, so the main idea here is you need a device that can remember what the previous value was. So we're going to use, this is called a D flip-flop, which also is known as a D latch. So have a look for one name or the other. Either it's called a flip-flop or a latch, depending on what catalog you're buying the part from or what simulator you're acquiring the part from. And it's going to have a data pin, a clock pin, and an output pin. So Q is your output, D is for data, and then this symbol here means the clock. And the way this works, the Q value will copy the D value whenever the clock transitions from low to high. Let me just quickly show you what I mean by that. Okay, so over here I've got, under sequential elements, this is a D flip-flop. It has several pins on it. We're only going to use 3 of them right now. We're going to use the data pin. That's always labeled D. The clock, and I'll just use an input switch to change the value at the clock. And then an output to see what's happening. Now the way this works, that data pin value can change, and notice the output value does not change at all. However, when the clock transitions from low to high, the output value copies the data value. So now that data value can change, and over here it's going to remember the value it had. Now that it's at 0, when that clock transitions from low to high again, it's going to copy the 0 that was there. And that data value can change, and nothing is going to happen until the clock transitions again from low to high. So we call that rising edge triggered, when the transition of the clock from low to high initiates the change. Okay, we're going to use 4 of these to represent the 4 binary digits here. And as you can see, and I've hid the details, but I'm going to show you how to do the first 2 least significant bits, and then I'll leave you to figure out the other 2. So watch as this transitions from 0 to 1, 2, and then finally to 3, and back down to 0. Of course, that's in binary, so for 2 we have a 1, 0, for 3 we have a 1, 1. Okay, now the first thing that we want to do is figure out our least significant bit. If you look at the least significant bit, notice how it's always transitioning from 0 to 1, and it's transitioning from 1 to 0. So the least significant bit changes every time we receive a clock pulse. So what I'm going to do is I want the data line to be the exact opposite of the output line. So I'm going to get a gate, and I'll use a NOT gate. I'm going to change the direction of it. And now I'm going to feed Q back in as the D value. So we can get rid of this. So now when our Q value is a 1, the D value is a 0. When the Q value is a 0, because of that NOT gate, the D value will be a 1. And now every time the clock transitions from low to high, this switches. So we're properly getting our least significant bit here. So a way of writing that out using a bit of Boolean algebra is we can put in some subscripts because we have the old Q value affecting the new Q value. So I'm going to say Qn for the new value, and it's equal to not Qn minus 1. So this is the new value, and we're making it the exact opposite of the old value. As you can see, when the old value is 0, the new value is a 1, and when the old value is a 1, the new value becomes a 0. Okay, so that takes care of D, which is the least significant bit. Now let's have a look at C, the second least significant bit. So the C value, if you look here, the C value becomes a 1 when the previous value was C was 0 and D was 1. See that? It also becomes a 1 and looks like when I was counting up, I missed one here. That should be a 1 there, actually. Yeah, because that counts up, that's 0, 1, 2, 3, 4. It also becomes a 1 when the previous two values are 1 and 0. So we get a 1 here if the previous two values are 0 and 1. And we get a 1 here if the previous two values are 1 and 0. So for C, I can write that my new Q value is equal to the old Q value for C and not the old Q value for D. See here, when D is 0 and C is 1, C is going to be 1. When D is 0 and C is 1, C is going to be 1. And that idea is captured in this expression here. When the old Q value is on and the old Q value of bit D is off, then it's going to be on. Or there's another case where it comes on. And that is when the old C value is off and the old D value is on. So I can write that as Qn minus 1C is off and Q at n minus 1D is on. So that's maybe this will look simpler if I just use C and D for those values. So your new C value is when your old C value is on and your old D value is off, or when your old C value is off and your old D value is on. So if we have C but not D comes on, if we have C but not D, that comes on, or if we have D but not C, it comes on. That's what I'm writing here. So we could use a mix of and, or, and not gates. However, if you're perceptive and you look at this closely, you'll see that this is just C and that is just D. So it's one or the other, but not both. And that implies that what we need is an exclusive OR gate. So exclusive OR looks like this, and it will come on if we have one or the other, but not both. So this will be on if we have C and not D, or not C and D. That's exclusive OR. So that's what we have to do for our second least significant bit, C. So whereas this one is just automatically transitioning, and that's my least significant bit, I'm going to drag it down here. For my second least significant bit, so I'll get another D latch, or D flip-flop it's called here, and I want my D value to be my old D value exclusively OR the old D value, the old Q value of the least significant bit. So over here I'm going to get an exclusive OR gate. And because the values are going this way, I'm going to reverse it. So under properties, I'm going to have this face left. And I'm going to use the output of this exclusive OR gate as the input to the second least significant bit latch. And I'm going to feed the output as one of the inputs and the output here as the other. So that's the old C value and the old D value are exclusive ORed and fed in as my input. Okay, so now let's just have a look at our output here. And then we need the clock to run this. So I can use an input switch as the clock. Okay, and now as that transitions, have a look at these values here. I've got a 0, 0, now a 1, now a 1, 0, which is a 2, and now a 1, 1, which is a 3. So your task now is to add two more of these sequential elements, two more D flip-flops. Put one here, and put one more right here. And then add two more outputs here and here. And then what you really need to do is go back to this chart. Have a very close look and figure out, ask yourself, under what circumstances does B turn on? And under what circumstances does A turn on? So have a look at the previous conditions that will turn on B, each of the previous conditions that will turn on B, and have a look at each of the previous conditions that will turn on A. Let me redraw this chart. I'll clean it up for you a little bit and then re-explain that. So you have your inputs, A, B, C, D. And we've got the numbers that go from 0 to 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, now we're trying to figure out, you're going to try and figure out when to turn on B. So you can copy what I've done so far, and that'll turn on C and D at the right time, so that that counts its way up from 0 to 1 to to 3. And then when does this come on for bit 4, and when does that come on to indicate an 8? So you've got the first time that bit B makes its appearance is here, and it comes after these. So I can say that B at n, so my current B, we get it when previous to it, B at n minus 1 is off, C at n minus 1 is on, and D at n minus 1 is also on. So I've taken care of this. Now notice I'm not really concerned about that because a less significant bit never really depends on a more significant bit when you're counting. So this is part of the expression, but I need to add or. I need to have a look at this case because this case will cause that bit to be on. And I need to look at this case. It'll cause that bit to be on. And then this case will cause that bit to be on as well. So there are 1, 2, 3, 4 cases where bit B is on, and you have to capture the 4 previous cases with a bit of Boolean algebra, do some manipulations, and then from there, I'm sure you can figure it out. So by the time you're done, you're going to have a circuit that will automatically count its way up. And one last thing you can do, instead of having a switch here, we can get a clock, and it's here as a sequential element. So you can tie this clock into the clock portion of each of the D latches, and then they will automatically transition. So this goes 1, 2, 3, and then back to 0, but when it goes back to 0, this can pop up, so it's a 4, and then it'll go up to 5, 6, and so on from there. Okay, best of luck.